Hi, folks. Today we're addressing an important question I get a lot. How can you tell if this is scientific misinformation? The this in this question is usually something that's been shared on social media. If you're interested in this topic, stick around, and I'll show you some things you can do to help you make that assessment for yourself, even if you aren't a scientist. Welcome back to the channel. If you're new here, my name's Greg. I'm a biology professor based in Singapore, and I've had a career in both biotechnology and academia. And on this channel, we explore a combination of scientific topics that interest me, as well as the important topic of scientific misinformation. At this point, it's a cliche to say that we are all continually bombarded with information, but it's true. Right now, at the end of 2021, much of the information onslaught is represented as scientific, and a lot of public focus has been on biomedical issues, because we've all been trying to grapple with and make it through a global pandemic. After one of my recent videos on scientific misinformation, a number of people asked me about whether some other story they had seen was also misinformation. I tried answering these questions. I tried looking into some of them, and I noticed that a lot of what I was doing was basically the same every time I wanted to check, and it's those things that I want to tell you about in this video. These tools won't decide for you if something presented as scientific is misleading, or if it should or shouldn't be trusted, but I hope that the methods I cover in this video can help you make that assessment for yourself. So first, what's the context in which this question comes up? I'm going to assume that the question of whether something is scientific misinformation comes up when someone has shared an article or a video on social media. The article or that video may also have some links to scientific papers or news articles about scientific papers, and it may have some quotes from scientists. Now, maybe you trust the person who shared it with you, or maybe you trust the social media setting in which it was shared, or maybe you trust the YouTuber or the podcaster who shared it in the first place. None of that matters. People sharing misinformation, whether intentionally or not, can appear trustworthy and they can appear well-informed. And well-meaning people can amplify scientific misinformation that they've received from others. This happens all the time. The question for each of us is whether we will be able to spot junk science or misinformation when it's being amplified and break the chain. The rest of this video is going to be divided into two broad categories of scientific misinformation, and I'm going to describe several tactics used that fall within each of these categories. The first misinformation category I'd like to describe is what I would call deceptive representations of science. This category involves deceiving readers or viewers about the authenticity or the provenance or the authority of something that is claiming to be scientific truth. This is a widely used misinformation strategy, and I'm going to describe three common tactics that are used within that strategy and how you can detect when those tactics are being used. The first tactic is using publications in bogus or predatory journals. The way scientific publication is supposed to work depends on a lot of volunteerism. Scientists perform research and write papers, but also serve as volunteer editors of scientific journals. When a manuscript gets sent to a journal, the editors decide if it looks like it might belong in that journal. And if so, they try to identify experts in the field who can read it and review it. A legitimate journal usually requires at least 3 peer reviewers for each manuscript. But people are busy, so editors typically send 6 to 8 emails to get those 3 reviewers agreed. Those who agree are sent the manuscript. They're given a few weeks to review it, write up their reviews, and return them to the editors, who then make a decision about the manuscript. The decision is usually some form of either accept, reject, or maybe please revise, in which case the authors are given a second chance, and the whole process is repeated with the information from the reviewers passed on to the authors. As you might imagine, the peer review process is time-consuming. I've been an author. a reviewer, and a journal editor, and there's a lot of work involved for everybody. Remember, these are all volunteers. Most of them are full-time academics. Developments in online publishing have changed a lot about how science is communicated. Much of this has been really great. It's increased access to the research literature. But there's been one pernicious trend, and that's been a rapid increase in pay-to-play journals. These are journals that pretend to be authentic. They pretend to be authentic, open access scientific publishing houses, but they take shortcuts in peer review, or they skip it altogether. Now, I'll use an analogy. Suppose your uncle shows up at a family dinner and announces that a wise publisher has finally seen the genius of his childhood poems and has agreed to publish them for a small fee of $10,000. Predatory journals are something like that. They charge authors under the guise of legitimate open access page charges, but skip the peer review process. And that's the process that protects the integrity of scientific publication. These bogus or predatory journals corrupt the scientific process, and they can be a conduit of scientific misinformation. So how can we identify them? Identifying publications in bogus journals is not always easy, but there are some ways that work a lot of the time. First, the very worst predatory journals are not indexed in professional scholarly indexing services. This means PubMed or Medline for biology-related journals, Web of Science for all areas of science, and Scopus for scholarship more broadly. If someone provides a link to a paper in a clearly predatory journal, they probably won't provide a link to PubMed because they can't. Instead, they'll link to the publisher. If you put the paper's title or the journal's name into PubMed or into Scopus and nothing comes up, it's a pretty good guess that this is a publication in a predatory, in other words, a bogus journal. Google Scholar is widely used, but it's not, in my experience, careful about this distinction, and so I don't recommend it to identify papers in predatory journals. Okay, does this always work? Not always, because there is some gray area, and there are some arguably predatory journals that are still indexed in PubMed. So you can also check journal names and publisher names on a website developed by volunteers to track predatory journals. This list dates back to an earlier list developed by the academic librarian Jeffrey Beall, famously called Beall's List. There may be some disagreement on particular journals, but at least it's a possible red flag. As always, there will be links in the description. The second tactic is obscuring retractions. Sometimes misinformation will circulate and it looks like a scientific paper, but it turns out the paper has actually been retracted. Like papers in predatory journals, when retracted papers are shared as misinformation, the person sharing it probably won't use a link to PubMed. But they probably won't use a link to the journal either, because either link would identify the paper as retracted. Instead, this kind of information will typically be circulated as PDFs of articles, and those articles will be uploaded on a completely different website. Even though retracted papers are used to spread misinformation all the time, they are relatively easy to identify, because you can just check the journal itself or one of the scientific indexing services like PubMed or Scopus. They will usually mark the paper as retracted. The third tactic under this first category of misinformation is pretending that something is peer-reviewed and amplifying it with that sense of authority. This tactic, which is really common for bleeding-edge scientific misinformation, is not using bogus sources per se. It's not deceiving people with bogus journals or hiding the retraction status of papers. Instead, this is a different kind of deception. This is typically something like circulating abstracts of posters from scientific meetings, or circulating research preprints as if they had been peer-reviewed. Let me give an example. There was a recent abstract presented at the scientific meeting of the American Heart Association. This non-peer-reviewed abstract, with a single author and filled with spelling errors, was picked up first by anti-vax groups and then circulated and amplified by widely followed social media influencers who should have known better. A large medical meeting will have thousands of abstracts, each of them often no longer than a single paragraph. At the meeting itself, the authors of each abstract will present their work on a poster, and people who are interested in it can visit that poster to discuss it with the authors. Poster abstracts are not usually peer-reviewed, and it is deceptive to present them as such. If someone is circulating an abstract without an accompanying paper, it is easily used for misinformation, and that's true regardless of the veracity of the abstract itself. This should be a red flag. Okay, so that completes the first misinformation category. The second misinformation category I want to cover in this video involves manipulating the message, or putting spin on science. This type of misinformation is really distasteful, and it's often unethical, but it's also easily amplified on social media. Here are 3 more misinformation tactics that fall under this category. The first tactic is science by press release. Sometimes a major scientific finding generates news interest. That's natural. Sometimes journals put out press releases, or universities put out press releases to coincide with a notable publication. But this is easily manipulated to put a political spin on and add political power to bad science. Let me take an example from early in the COVID pandemic. In April 2020, a group of scientists, many at Stanford University, published a preprint analyzing the presence of antibodies to the SARS-CoV-2 coronavirus, and thus estimating the number of people who had already been exposed to COVID. This was done in Santa Clara County, California, and was used to further estimate the IFR, or infection fatality rate, from COVID. At the same time the study appeared on a preprint server, and remember, this had not gone through peer review, the study backers and authors organized a publicity campaign around the policy implications of the findings. They used op-eds, they appeared on television shows, and so on. The basic message of this spin was that the seroprevalence, or the antibody detection, was high, and the estimate of infection fatality rate was low. This was picked up by conservative media outlets and pundits to argue against lockdowns because COVID was so widespread. Now, all of this happened at the exact same time scientists were first reading this study. And the study, it turns out, was terrible. It made basic mistakes in statistical methods. These were compounded by not having an appropriate expert involved in the study. It was almost surely subject to selection bias because of the way recruitment was done. It had multiple undisclosed conflicts of interest in funding and authorship. The authors didn't provide access to the data or the code, and on and on. As the well-known statistics professor Andrew Gelman of Columbia University described it, I think the authors owe us all an apology. I think the authors of this study owe an apology not just to us, but to Stanford. Okay, so what to do for you and me? If you see a scientific study, especially a preprint study, that is accompanied by an organized publicity campaign, op-eds in newspapers, pundit commentary, the best thing to do is wait. Wait at least a week or two for experts to evaluate and critique this study, or for conflicts of interest to come out, or for funders to be disclosed. If it holds up, there's no harm in having waited. If it turns out to be a source of misinformation or manipulation, at least you won't have been contributing to it. The fifth tactic is oversimplification and amplification by influencers. This is very common in misinformation on social media, and the idea is to distort an analysis, and typically that distortion is an oversimplification, and then use pundits and social media influencers to amplify that distortion. As an example of this, I want to use a headline from August 2021. That headline was, nearly 60% of hospitalized COVID-19 patients in Israel fully vaccinated, data shows. Now, Israel had been ahead of many other countries in vaccinations. And this was derived from an Israeli government data dashboard, and it was used to push the false argument that the vaccines weren't protecting people from hospitalization. And it seemed plausible at first. Just look at this table that summarizes the argument. Now, this table was made by Professor Jeffrey Morris, who created it to show that it is wrong. Jeffrey Morris has done a beautiful analysis of this. The misinformation about the Israeli vaccination data is an example of something called Simpson's paradox, which is a paradox in statistics and probability. And the problem is because the unstratified data, the oversimplified data, is deeply misleading. Let me give an example that I use when I teach Simpson's paradox. If you have some data on two variables like this, the x and the y variable, you can draw a line to represent the association, and it might appear that there is a positive association between the variables. But if you knew the subgroups, you can immediately recognize that the association is negative within each subgroup. That is exactly the opposite relationship is really there, but it was missed because the original oversimplification missed the existence and the importance of those subgroups. The same flaw is the case for the Israeli vaccination data, because the numbers in that table aren't stratified by age and they weren't adjusted for population size. Once you account for those variables, as Professor Morris shows, the vaccination efficacy against severe disease is overwhelming. But ignoring the effects of Simpson's paradox has been used, intentionally or not, to misleadingly undermine public understanding of vaccine efficacy. Now, I don't have an easy or straightforward tool to use to push back against this kind of misinformation. But there are some good questions to ask when you see a figure or table that is sending a potentially misleading message. You can ask, what are they not telling us? Or what's left out of this figure that may be distorting or oversimplifying the interpretation? The last misinformation tactic I'm going to describe is what I call stealth, agenda-driven pseudoscience. In much the same way that predatory journals imitate legitimate scientific journals, fake pseudoscientific websites imitate legitimate scientific information sources. A really good example of this kind of misinformation is the IVM Meta website, which poses as an unbiased, ongoing meta-analysis of ivermectin use to prevent and treat COVID-19. It looks authoritative, and it looks well-designed, and it looks dispassionate, and it looks scientific. But any experienced outside expert in meta-analysis can quickly recognize how the analyses on the site violate all the conventions and best practices of good quality meta-analysis. It seems pretty evident that all of that practice on the IVM Meta website is done for one reason, and that's to ensure that the results come out in favor of ivermectin. The people behind the site are anonymous. They don't handle risk of bias or study heterogeneity properly. They combine analyses improperly, and so on. It's just a mess, and it's all misinformation. In fact, in this case, it probably qualifies as disinformation, since it's hard to imagine the deception of the IVM Meta website isn't intentional. This kind of deception on pseudoscientific websites is probably the most difficult to identify without specialized expertise. And honestly, even some widely followed scientific YouTube channels have been fooled by the IVM Meta nonsense. But I encourage you to ask a simple question or two of any site claiming to be an objective scientific analysis. First, is it anonymous? Is its provenance uncertain? If so, treat it as a probable source of misinformation. Now, if you're curious, Dr. Susan Oliver has created an excellent video discussing the many flaws of the IVM Meta website. And you can find a link to that up here. Okay, if you've stuck around this long, I want to wrap it up. And there are lots of types of scientific information that I haven't covered here, and there are lots of types of non-scientific misinformation or disinformation. I've mostly used the word misinformation here because many people spread it without any intent to deceive. I use disinformation for the IVM Meta website because I don't see any way to view what's going on in that site as having been made in good faith. If you have questions about spotting misinformation, please leave them in the comments below. If you've found this video useful and of value, give it a like, share it with others, or let me know in any way you like. And I will see you in the next video. Stay safe, everyone.